Hi, everyone. Welcome to the Earth Engine virtual meetup. We're really excited to have you here. And today we have a special guest with us. We're also live on YouTube. Please head on down to the YouTube channel at bit.ly/euvm-youtube, and you can see the live stream that's going on over there right now. And our special guest is Jennifer Hurd from the University of Calgary, who will be speaking today about harvested forest regeneration from space, leveraging Google Earth Engine for large-scale analyses in Alberta in Canada's changing landscape. So we're really excited to have Jennifer here today with us. So right now I'm gonna turn the screen over to her so that she can share her presentation.
Okay, sounds good. Thank you, Sabrina. I will share here. Okay. In the interest of internet, I'm going to turn my video off here while I'm presenting so that that doesn't interfere here for me. Okay, so I will get started then. Thanks everyone for joining. I'm really glad to be here today. I've been to a number of the Earth Engine virtual meetups over the months, and I've really enjoyed them. So I'm glad to be able to come and share what I've been doing with Google Earth Engine with all of you. So as Sabrina said, I'm going to talk about some work using Google Earth Engine and looking at harvested forest regeneration from space from using Landsat data. So my name is Jen Hurd. I am a remote sensing scientist. I work in the Geospatial Center at the Alberta Biodiversity Monitoring Institute. That I based out of a lab in the geography department at the University of Calgary in Alberta, Canada. And you can see at the bottom there my email and my handle on Twitter if you ever want to reach out or see what I've been up to lately. And without further ado, I'm going to get started. Okay, why is this not working? Going to the next slide. Okay, here we go. Okay, so today I'm going to talk to you a little bit about the Albertan landscape and forestry on the Alberta landscape, just to give you a bit of background on that. And then I'll talk to you about my methods and how I've been using Google Earth Engine, a little bit step by step through the different pieces that go into all of this work that we've been doing. And then I'll talk about our final data set, what came out of all of this work that we've been doing. Some final remarks, and then I created at the end of December a simple but a new Google Earth Engine app. So I was going to show that to you and share that with you. I will, at the end of the presentation, I will copy and paste the URL into the chat so that folks can go and explore it on their own too. Okay, so we'll get started with Alberta. So Alberta is in Canada. In Western Canada. It is a fairly large place. It covers over 660,000 square kilometers, and it has a landscape that is constantly changing, both with anthropogenic and natural changes that are going on the landscape. We have a lot of agriculture in our southern prairie regions of the province. In all across the province, we have oil and gas well sites and other facilities and things going on. We have forest fire. We have a lot of forests, and fire is one of the major drivers of the forest ecosystem and change in the forest. So that's always happening. We have forest harvest going on, which is what I'll talk about a little bit more. This is an oil and gas facility up in northern Alberta. And then we also have other natural changes like pine beetle going through the province. So there's a lot going on in the landscape. So it's important for us to be monitoring and mapping these changes as they're happening on the landscape. And that's one of the big motivations behind a lot of the work that I do. Now, Alberta is 60% forested, so there's a fair amount of forest, boreal forest. And Alberta has a long history of forestry. Before it was even a province in Canada, there was forestry going on in the landscape in Alberta. So Alberta is a world leader in sustainable forest management. The Forests Act lays out specific policies and regulations and guidelines on how forests are to be managed within the province. And this means that reforestation in those areas that are harvested is the responsibility of those who are harvesting those areas. And those companies who are managing those forests and reforesting those areas then have a good local level knowledge of regeneration in these areas and reforestation. They monitor them, they understand them well, and they're managing them for the long term as in their own interests as well, because they want to be able to harvest again later as well. But this local level knowledge is proprietary and is local and site specific. So it doesn't translate into regional or provincial level knowledge of regeneration patterns across the province. So our goal has been to leverage the open access satellite data streams that are available and cloud-based services like Google Earth Engine to spectrally characterize general regeneration trends in harvest areas across the province. So we are using the Landsat archive, Landsat 5, 7, and 8 imagery from 1984 until the present. We're using, in order to identify where harvest areas are, we're using something called the Human Footprint Inventory. So the organization that I work for, ABMI, creates this human footprint inventory that's this digital representation of human footprint all across the province. And it's a very comprehensive database with a lot of different types of features in it, and harvest areas are one of them. And so we're using that to build our workflow. And then, of course, I'm using Google Earth Engine. Now, I work in the online JavaScript API for everything that I do. And I hope that one day I can expand into the Python API. There's a lot of capability there that I'd love to explore too. So why Google Earth Engine? I'm sure a lot of you have similar reasons for using Google Earth Engine. In Alberta, it's such a large place that it requires a lot of imagery to cover the whole province. There are 48 Landsat tiles required to cover the province. There are multiple decades of imagery, and with multiple images per year for multiple sensors, this adds up to a lot. So with what we've been doing, it would equal around or just about 20,000 images and almost 14 terabytes of data, which is not something that we could do on local desktop computers. We don't have the resources for that. So this is where Google Earth Engine comes into play, and especially it being a free service for educational research purposes, which is what we use it for research. This makes it really accessible for us. We're a nonprofit organization, and so using subscription-based pay-for-service type services would be pretty costly for us. So this is fantastic that Google Earth Engine has come along to help us out. So before I'm going to talk about kind of how we go about doing this, I want to just give you some information on what I'm talking about when I'm talking about spectral regeneration. So spectral vegetation indices, I'm sure a lot of you have worked with them or familiar with them. Some of you maybe less so. But spectral vegetation indices are commonly used for mapping and monitoring vegetation, and they combine bands from different wavelengths, often in the red and the near infrared, and sometimes shortwave infrared portions of the electromagnetic spectrum into an index that responds well to changes in vegetation. So what we've been using is something called the normalized burn ratio, which is very much like the normalized difference vegetation index, except that instead of near infrared and red visible, we're using near infrared and shortwave infrared in that calculation. And so this particular spectral index has been used a lot for looking at forestry and, forests and disturbance and regeneration in particular. So when I'm talking about spectral regeneration, what we're looking at is the return of spectral signals to pre-disturbance levels. So we recognize that this doesn't equal on the ground ecological function or return to the same composition or structure or successional stage of the forest on the ground at that time. It's reflecting a broader change in the spectral signals in those forested areas. So here's sort of an example time series of normalized burn ratio over time for a particular pixel. So here in 1985, you see the true color, and then the NBR index. Brighter colors, of course, are brighter grays are a high NBI value, or NBR, sorry, value. And then in 1984, we see that area has been harvested. We see the drop in the NBR. We see that in the imagery that has been harvested, the forest has been removed for harvesting. And then later on in the time series, as the signal comes back, we see that greenery is returning, vegetation is returning. By this time, I'm sure there are saplings and things on the ground there, and you see an increase in forest structure and greenery that goes along with this increase in the normalized burn ratio. So that is the basis on which we're extracting or looking at regeneration in forested areas. So the sorts of things that we extract from these time series are things like, we look at what the signal was like before the harvest. We pick 5 years before the harvest and take an average NBR value. We look at where that signal drops that corresponds to a harvest. And because we're using a digital database of harvested areas, we know that looking in those areas when we see a disturbance, it's almost surely to be a harvest happening. We look at how much the signal has changed with that disturbance. We look at where the signal's starting to come back. That's the start of regeneration. We look at where that signal is 5 years after regeneration. And we look at how many years it takes for that signal to get to 80% of its pre-harvest levels. And those two metrics, the 5-year regeneration and years to 80% regenerated, are metrics that are found in the literature and shown to work well for this sort of work. And have been related in I think Finland with on the ground vegetation or tree cover and height. And then we also look at where the signal is currently, so a current level of percent regeneration, percent of the signal that has come back. And this can actually exceed pre-harvest levels because it's reflecting the changes in the structure of the forest. And a mature forest that's there before harvest has a different structure and composition than what grows back a lot of times, or than what's there in the early successional stages that would be represented, say, 10 or 20 years after a harvest in our spectral signals. Okay, so here's what we did. So we took Landsat 5, 7, and 8, as I said, we used the surface reflectance products from Google Earth Engine and brought them together. This code is actually a snippet out of Landtrender. We used Landtrender, which I'll mention in a little bit here. This is a code that they use to bring these collections together into a single collection. We used the flags to remove cloud and shadow with the QA bits. And then we calibrated Landsat 8 to match Landsat 5 and 7. And this is a code that's also in the Landtrender algorithms that's based on a published method that's in the literature by Roy and others, 2016. So this just brings the Landsat 8 over to match with the bands of Landsat 5 and 7 so that we can combine them all together. Then we bring all of this image together into one image collection, and we create annual composites of growing season median pixel values. So for each year, we take the imagery from June until September, and after all the cloud and things have been masked out, and we take a median value for each pixel for that year, and that represents that year. So we get these annual composites that are representing sort of general greenness for each year in that pixel. We calculated the normalized burn ratio. So as I said, we use near infrared. So we use band 4, and then we use band 7 shortwave infrared from Landsat. This is the calculation for this particular index that's used in the literature. And then we applied that Landtrender algorithm. So Landtrender, if anyone isn't familiar with it, is a set of algorithms that was developed out of the University of Oregon. And they it's a method that takes a time series and breaks it up into segments that are represented by a regression line. So it temporally segments a time series, and it minimizes noise within those segments. But using the multiple segments can capture the different trends and changes that are happening in the signal. And it was designed specifically for looking at changes in forested landscapes, especially. So it works well for what we're doing here. And then we extract a series of metrics, as I showed you in that example from the fitted time series. So here's sort of an example of a snippet of code looking at the pre-harvest values. So taking an average of all of the normalized burn ratio values for the 5 years before a harvest was detected, and using that to represent the pre-harvest signals. Some other metrics, another code snippet that we used here. This is total regeneration. So looking at what the spectral signal is like at the very end of the time series versus compared to, you know, how much it had dropped with the disturbance. And I'm sure pieces of this don't make a lot of sense unless you see the whole code, but the whole code is very long, so I wasn't going to put it all up here. And then we also used some masks to remove unwanted pixels. So we wanted to make sure in these harvest areas that we weren't using pixels where you don't have a harvest. In harvesting in Alberta, there can be retention, so they will leave patches of the forest in there. And we don't want to use those pixels in looking at harvest regeneration, or in some places you might have a well pad come in and you don't have regeneration going on that well pad because it's in use. And so we don't even want to use those pixels. And sometimes you have multiple disturbances. Forest fire, as I mentioned, is common in Alberta forests. So I've seen areas where you have a harvest and then a wildfire comes through a number of years later. So you have multiple disturbances on the landscape. So we removed all those pixels that represent more complex things that are going on the landscape than simple harvest area regeneration, so that those weren't in our analyses. And then we exported all these different metric layers that have been masked for those particular conditions to assets. Oh, sorry, not Google Drive. That's a mistake in the slide. To assets, so that we could use them to actually then extract for these harvest areas. We bring in the polygons and use reducers to look to extract mean and standard deviation of the various metrics over all of the harvest areas, and then export that to Google Drive from Google Earth Engine. And then I don't know if any of you really have worked with those sorts of exports. It spits out a big CSV file, and it needs to be reformatted in order to be used. So that's where we bring it into R and reformat the output into a table that kind of makes sense for our purposes. And then I removed data where I had a low confidence in the output. So with that masking, you can have harvest areas where more than 50% of the harvest area has been masked out for whatever reason, whether it's a fire or retention or various other things. And so I wanted to make sure that the harvest areas that remained in the data set were well represented by a sufficient number of pixels. So I removed ones where I didn't have a lot of confidence in the output, and then brought all of that back into ArcGIS. That's where I pre-processed harvest areas. When I say back into ArcGIS, I bring that table into ArcGIS, and we have a provincial wildfire database that is an up-to-date database of where wildfires that have happened on the landscape over the years. So I use that to remove any additional harvest areas that were affected by wildfire, but that may not have shown up for one reason or another, or not been captured with the flags that we were using. And then we also have overlapping human footprints. So I also removed human footprints or harvest areas that were affected by other human footprints. So there are some areas that are harvested and then later are mined. They end up being areas that are mined later. So we wanted to, so those don't represent harvest regeneration in those areas. So we removed those as well. And then we came up with this final data set. So the latest human footprint inventory that ABMI has is updated to 2018. They're working on 2019 now. And so those are the polygons we use. So we extracted spectral regeneration to 2018. And we used imagery covering 1984 to 2018. So this is sort of a map of the areas that we analyzed. A lot of harvest areas were harvested before 1984, and we didn't look at those areas. So in the original database, we have over 232,000 harvest areas across the whole province, and this represents harvest areas that are range in age from the early 1920s up until recently. So there are a lot of, this represents quite a history of harvesting in Alberta. With pre-processing of the harvest area polygons, we did some buffering and some simplifying of outlines, and some were then too small for a Landsat pixel, so we removed those. So we brought in 177,000 of them into Google Earth Engine, and our final data set has just under 58,000 harvest area polygons with information on spectral regeneration. So a bit about that data set. I already mentioned those. The harvest areas themselves do range in size quite a bit, from around 2 hectares to well over 500 hectares. So it's quite a variety of harvest areas across the landscape. On average, after 5 years, harvest areas reached about 60% of their pre-harvest signals. This is an average over 57,000 harvest areas. So the standard deviation, if I remember correctly, was about 18%. So there's a high standard deviation because there is a lot of variability in the data set. On average, it takes 8.7 years for harvest areas to reach 80% of their pre-harvest level spectral signals. I think the standard deviation here was about 3.5 years. So there's also a lot of variability in that metric, which is understandable. It's covering all of Alberta, which covers quite a latitudinal gradient as well as an elevational gradient. We've got the Rocky Mountains in the west and prairies and lowlands more to the east. And in the data set, we have 68% of our harvest areas have reached 100% of their pre-harvest spectral signals, which isn't surprising since it covers it covers 3 decades, our data set, and spectral signals do come back relatively quickly. Here's an example area of the data sets, what they kind of look like on the landscape here. You might notice, if you look kind of more closely at it, there are different patterns between the 5-year percent regeneration and years to 80% regeneration. There are differences. They are both looking at spectral regeneration, but they're measuring different things. They're representing different processes on the landscape. The 5-year regeneration is early successional stages, and years to 80% represents later regeneration, not late successional stage, but later regeneration. And spectral signals, it isn't really a linear trend up. There is it does plateau at a certain point. So there are different relationships here. So alongside our data set, which we published on the ABMI website, the ABMI website is just abmi.ca. I thought I had a slide on that in here, but maybe I missed that. We also created this little app so that users could go in and just kind of look at the data and browse a little bit of it and see what it's like before they go ahead and download it. So I was going to show that to you after the presentation here. I'll paste that URL into the chat for you. So our next steps with this work is to take this and conduct an analysis on spectral regeneration and environmental factors across Alberta. No one's ever really done that across the whole of the province before. So looking at how spectral regeneration varies with climate anomalies, with local topography and things like that. So we're working with some collaborators and working on the analysis and starting to write the manuscript. And this is some really neat stuff. I'm really looking forward to seeing how this turns out. So that's some exciting work that we couldn't have done without this data set and Google Earth Engine to help us out. And of course, we recognize the importance of linking this with what's actually going on the ground. So we're starting to get into some comparisons with existing ground data. We have some Alberta permanent sample plots, which are government sample plots that are revisited over the years across Alberta's forested areas. We've got some collaborations with some folks in government, and we've been able to access some of that, which is great. And then ALPAC is Alberta Pacific Forest Industries. That is one of our leading forest industry companies in Alberta. And they've shared some establishment surveys. So they go in, I think establishment surveys are between 5 and 10 years after harvest. And they go in and they look at how much is, what the seedlings are doing and how much, what the density is and things like that. So we're starting to make some comparisons there too, which is exciting. And then the next step after that with ABMI is expanding this approach to other types of human footprint features. We started with harvest areas, but we also want to look at other human footprint features on the landscape because there are so many different types of features across Alberta, and we want to be able to look at those changes and how things may be following patterns we expect or maybe not coming back where we think they should be. So right now that work is focused on mined areas, like reclaimed mined areas and well sites. The ABMI is part of oil sands monitoring within the province of Alberta, if anyone's heard of the Alberta oil sands. And so this work is focused in that area and looking at specifically features that have been reclaimed and brought back to an equal ecological function to what was there before. So that's some cool stuff too. That's just in preliminary stages. So with the help of Google Earth Engine, we've been able to leverage this long-running continuous Landsat archive over the scale of Alberta and over multiple decades, which is fantastic. And we've been able to develop this repeatable workflow for characterizing spectral regeneration in harvest areas across the province. And we've been able to publish a public data set for anyone to use with that. And because this is repeatable, we can update this as new harvest areas come in and as we get more Landsat data coming in over time as that builds. So that's exciting. And then not only is that data set public, but we're now able to use that for some further research and analysis that can help us to inform on broader patterns of regeneration across the province, things that no one's really been able to look at very easily in the past. And then we're using this workflow to start looking at other human footprint features, which is also some exciting work. Okay, so those are all my slides. Thank you for tuning in, for your attention. What I'm going to do is I'm going to now switch over to Google Earth Engine and bring up this app. I'm just going to refresh here. I will take this URL and put it into the chat. See, there's some questions. We'll get to questions certainly here after I've given you a bit of a demo here. So this is the app. It's a little squished here on a laptop screen. It's better to look at on a bigger monitor, but it still works here. So we have year of harvest that was detected. We have 5-year spectral regeneration, total spectral regeneration to 2018, and years to 80% spectral regeneration. So we can actually scroll through the map. So the gray harvest areas are harvest areas that either weren't harvested at the right time or their data wasn't reliably extracted. And then the ones in color are the ones that we have metrics for. So you can scroll, you can zoom in and out here to look across, and this will cover all of Alberta. So there's a lot here. And then you can also click on a harvest area, and it takes a minute to generate and bring in the metrics. It usually gives a message saying it's calculating, and I'm not sure why that's not coming up. Oh, it is. It's just being slow. It usually, I think my internet is not great right now because it usually also highlights the, there it goes, highlights the polygon that you've clicked so that you can look at it and compare it across the 4 different maps and look at what regeneration is looking like here. Okay. I also was going to share a little of the code that went behind this very quickly. This is building an app. This is the first time that I've built an app. So it's something, it's a different experience for me in Google Earth Engine, working with the graphical user interface functionality. I thought it might be of interest for people to look at. So what I do is I bring in my data set from an asset. I import it here, and then I use it to look at those that have metrics, and then the rest of them to provide that sort of gray layer of other harvest areas. So the different steps in here are creating each of the maps, setting the various settings, adding labels and other things in here. So each map is created and set up in here first. Then there's code that I borrowed from elsewhere online that showed how to create that gradient legend on the map. So I've got code in here that creates legend for each of the maps. And then the next piece is to set up the different panels. So setting up that grid of the 4 panels on the screen in there, and controlling what buttons come up. So whether there's a zoom button, whether there's a scale, you know, the plus and minus, zoom in, zoom out buttons and things like that, you can control all of that in there. And then creating that side panel that's on the left that has all of the information that populates when you click on a polygon in there. And the info boxes. And then adding all of that into the panel, and then creating these different map layers. Adding in those messages I have in there. So if you click on a harvest area that's gray, it will give you a message saying, please click on a harvest area or a feature that's shown in color, because there aren't any metrics for the ones that are grayed out. And then creating the callback functions for when you click a harvest area in here, and setting the visualization, highlighting things in red and that, and then setting those to callback functions in there. And then adding it all to the root map, and then yeah, and then it creates this neat little graphical user interface, and then this will then this code gets transferred into an app, and then it's an app that you can share. Okay, so I think that was all I was going to show you today. So I'm happy to answer questions here. Sabrina, would you like me to kind of start with questions that are in the chat?
Sure. I'm going to also, because we have some users who are tuning in via YouTube, so they won't be able to ask a question because they're not in the chat room. So we do also have a different question posting service we can use. So may I take the screen?
Yes, of course.
So thank you so much again, Jen. This was a really, really detailed presentation, and I really liked to see how well commented your code is. It's very clean and very understandable, and I think a lot of people will really appreciate being able to have the chance to take a look at that beautiful code. So we are using slido.com, which is a place where you can post your questions. So if you head on down on your browser to slido.com and type in the event code, which is hashtag EEVM, it will take you to the place where we can post questions, and people on YouTube can also interact with us. So let me switch over to the question place, and then we can start taking a look at some of the questions there.
You know, I comment code for myself just as much for anyone else, because when I come back to a code months after I've written it, I don't always remember what I was doing.
All right, so I think it takes a while before the questions will appear when people start asking them on Slido, but we do have a few questions here already in the chat. So I will read out the first question, which is why use NBR?
Sure. Yeah, that's a good question. So the normalized burn ratio was developed first to look at, as the name suggests, look at burn severity in after forest fires in forested areas. So it was used in that context, and then applications kind of broadened to other applications in looking at forestry. So if you mean why NBR instead of something like normalized difference vegetation index, or NDVI, the NBR responds to changes in structure and moisture, mostly in the vegetation and in the soil. And it tends to saturate more slowly than something like NDVI that uses red and near infrared. By using the shortwave infrared and near infrared, it captures more of that structure and moisture than just photosynthesis that's going on. And so I find that it saturates a lot more slowly than NDVI, and it seems to be less affected or less noisy than, I think, atmospheric effects, at least slightly, than using red visible in there. So those were the main reasons that we chose it. It's well used in the literature as well, so that helped support our decision in using normalized burn ratio. I hope that answers the question.
Thanks, Jen. We have another question from Emil from Slido. He's asking, how does phenology, e.g. leave off, affect the evolution of your spectral indices?
And that's a good question. We've hopefully removed most of the effects of phenological differences in our method because we're focusing on the growing season, and we're removing any winter or even like late fall or early spring imagery where you'd have very different phenology. I have noticed, though, saying that there is some noise in the signal between different years that reflects those median pixel values, kind of representing more, I guess, a different phenological phase. When I look at the Landsat composites in true color that come out of that method, sometimes you can tell that the pixels have come from a later phenological stage. You see less green, and I do notice that the signal is lower in those cases. Those changes, though, at least for what we're doing here with harvest areas, don't interfere with us detecting a harvest and looking at that strong signal change. So there is some effect from phenology, and in our case, it's noise for what we're wanting to do. But I think we've minimized most of that noise in there. in using the methods that we do.
And we also have a question here, Jen, which is a little bit more about how you accessed Google Earth Engine. So the question was, I wonder how difficult it was to get full access to GEE as a research institution.
That's a good question, and it wasn't difficult at all. Just as any of you, I use my personal account. So I asked for access as a member of the ABMI and said, this is who I work for, this is what I do, and I had no trouble getting access. The ABMI does have an official Google Earth Engine account, and that's where they host any apps that they create. And I actually wasn't part of setting that up, but I believe that they also got through Google Earth Engine a greater Google Drive space and to work with. And I'm afraid I wasn't part of those negotiations or how that worked. So I'm not sure how that side worked. So I had a colleague who did that. But I don't think it was difficult to get at least the access and the account set up for a research institution.
Thanks, Jen. So we have a question again from one of the viewers in the chat room who is interested in carrying out similar research on the Western Ghats in India, and they would like to ask for a block diagram or a method. I know you're in the process of writing a collaborative paper, so I guess part of that will have to wait for the publication. But would you be willing to share maybe your slides so they can take a look at your process?
Sure. Yeah. I'd be willing to share my slides. I didn't have them here, but I have some slides from other presentations that are a bit more detailed in terms of a workflow diagram. So if you want, you can email me that question, and I can respond and share some of that. I'm willing to share that. Anything that ABMI does is we want to be transparent and open with everything that we do. So I have no problem with that. Yeah.
Thank you, Jen. That's really awesome. So here we have another question from Slido. Will asks, hi Jen, great talk. How are you developing algorithms and fine-tuning, i.e. looking at individual tiles in color or indices? Are you looking at trends in R or other ways?
Yes, thanks, Will, and hi. I know Will. I'm glad you were able to tune in. It's a good question, and it's a combination of things. I do a lot of visualizing things in Google Earth Engine and visualizing the time series that went into those calculations with the mapping in the console in Google Earth Engine. And it's taken me time to kind of fine tune those approaches to looking at the algorithms and fine tuning them. But I will also export things, samples of things, and look at them in R as well to get a better idea of what's going on. So it's a combination of both. It takes some innovativeness, I would say, in really making sure that Google Earth Engine is doing what you think it's doing and what you want it to do. Definitely. I hope that answers your question.
Thanks, Jen. You have a lot of thank you messages from people in the chat room, and they're really grateful for the great presentation and the great work that you're doing. I really also love looking at the app that you made, and I'm curious about how users in the forestry industry and other people who are working with land use and land use planning are using the data set that you have created. And have you interacted with practitioners or policymakers or industry folks who want to use your data set to learn more about how the landscape is changing?
Yeah, that's another very good question. So we have had conversations ongoing over the last year year and a half at various times with various stakeholders. So sometimes with forest industry representatives, a lot of times with government folks actually, because they're more interested in the broader monitoring, and with various levels of government, forest industry, resource managers, and other people in the province. And we trying to understand, what they can get out of this and what we can offer. And I think from a forestry industry perspective, they already have a lot of good data on their own within their particular management units. So I don't know how, I think this might be useful in looking at a broad area. So that one forestry company that I mentioned, Alberta Pacific Forest Industries, has a very large forest management area. It's, I don't know, must be like a fifth of the whole province. And so I think they're interested in a broader sort of monitoring or reporting context, in looking at what's going on in general across their landscape. In looking more specifically, this isn't a data set that's going to help them. But on the other side, the government also, folks that we've talked to want to also are hoping to use this to build some tools to look at identifying harvest areas that are doing poorly, that are not meeting expectations, at least spectrally, and then they can use that in order to direct their on the ground efforts when they go and do QA QC, or they go and do their auditing and look at what's going on the ground. They're hoping that this can help direct them and make those decisions more effective for them in targeting those areas that need a bit of help. I hope that answers the question.
Yeah, definitely. And I think having an app that can be shared with external users can really help people gain access to that data set and interact with it more easily. So I think that definitely increases the impact of the work that you're doing, in addition with these meetings and stakeholder engagement sessions.
Mm-hmm.
Yeah.
So that knowledge that information to knowledge transfer process is an important piece of what AVMI does, for sure too.
Yeah, and I think the management data for those management units, if the various forestry companies are willing to share them with you, could be also really good training data to see how well it matches up to what you see with the Landsat imagery.
Yes, very much so.
Yeah, so thank you once again, Jen, for this really awesome talk and presentation. We are now going to open the floor to general questions from the audience. We usually have a troubleshooting tips and tricks session right at the end, where people can post general questions about what they're working on, and others in the community can try to answer them and give them a hand. So if you have any questions, feel free to post them either on Slido or if you're in the chat room here in Zoom. In the meantime, I have a few questions for everyone here. So here is the first question. Like what Jen said, she's mainly a JavaScript user and wants to explore the Python API. What about the people here? Are you all mainly JavaScript or Python users? Do you use both? Or are you new to Earth Engine and you're not sure where to begin? So feel free to answer the question on the poll here. I know I personally started with JavaScript because it was really easy to learn and also see the results directly in your browser window. So that's where I began learning how to use Earth Engine. And then later on, I started to dabble a bit on the Python side as well. But I still mainly use JavaScript even today. Yeah, all right. So most people are JavaScript users, and then we have a bunch of people who use both, and then Python users are at 13%. Right. And then I have another question, which is what topics are you interested in? Because we're just at the beginning of the new year, 2021, I would like to hear from you what are some topics that you would like to learn about? It can be subject area topics such as public health or atmospheric data, or it can be skills like how to make an app, how to use, like someone said, machine learning. So feel free to give us a bit of feedback so that we can invite speakers who might be able to help talk about these topics. A speaker, you're definitely welcome. This is an open space for any users in the Earth Engine community to showcase your work and ask questions and help each other. So please let us know if you're interested to be a speaker sometime this year. All right, looks like there's a large demand for SAR and land cover change as a topic. All right. Machine learning, public health, yeah, great. Thank you so much for sharing that. So before I turn back to the Q&A, I just wanted to let you all know about our upcoming talks. So in a month's time, we're going to have Celio Helder Sousa and Liza, sorry, I have a typo here, Liza Goldberg. She will be joining us and telling us more about her work as well, together with Celio at the NASA Goddard Space Center. And then in April, we are really excited to have Emil Charrington, who many of you might know as at BZGeo on Twitter, from Surveyor West Africa, to come and share about his work. So we're really excited to have two great sessions lined up for you, so please join us again. And in the meantime, I'm just going to head back here to the questions. And it looks like we do have another question for Jen. So Hadi asks, thanks, Jen, excellent work. As you're working with a pretty large area, can you share a bit on the data size, e.g. land render output and compute time required? Jen, I'm not sure if you're still here. Would you be able
Yep.
to share a bit on that?
Yeah, no problem. That's also a good question. I have run into limits on computation time and memory in developing this workflow. When I output, I'm trying to remember file size. At first, when I was first developing this, I would kind of create these metrics and then do the sort of zonal statistics at the same time within the same code. And that running those could take for a chunk, say of, what did I break it down into, say 20,000 to 30,000 of the harvest areas, that could run for a day. That would take a while. When I started exporting the assets to Google, exporting to asset, the different layers, it would, a different layer would probably take, I think it could take a few hours, but then actually calculating the zonal statistics didn't take, I don't think that took longer than an hour, but I would do it chunk by chunk. So I would export sort of each layer one at a time so that I didn't run into those limits. And then I would run the reducer, the zonal statistics on each metric layer one at a time. So that's where, for me, I think Python would be nice in order to be able to get some batch processing going on. But I've certainly had to break things down. But yeah, as far as output data size, I've had outputs that are, I'm trying to think, at least close to 100 megabytes. When you've got a very large data set, it's usually broken down into chunks. So I don't know what it would be for the whole province, but certainly even when I'm sampling small areas, say 1,000, let's say 1,000 to 2,000 polygons, and then looking at maybe 5 or 6 metrics, that could produce like a 6 to 10 megabyte file, a CSV coming out of that. I don't know if that, hope that helps to answer the question. It really varies based on how I break things down, but it's certainly, there are some big file sizes in there, and I've had to break things down in order to get around limitations.
Thanks, Jen. And someone posted a tip that it looks like gradient boosted trees are now available on Earth Engine. So that's also exciting news. And yeah, so I'd like to ask if anyone else has any questions, feel free to post them either in the chat or on Slido. And also please share your Twitter handles if you're on Twitter so that we can also stay in touch. Our hashtag is hashtag Earth Engine Virtual Meetup. And don't forget to also use the hashtag EOChat if you'd like to get engaged with the EO Earth Observation Chat community on Twitter. And thank you very much to everybody who is joining us once again. So if you have any questions, we have a couple of minutes left. Please feel free to post them, and we'll try to answer them as best as we can. All right, it looks like it's pretty quiet here. I don't see any more questions coming in. So I just want to end our session here with another really big thank you to Jen for the great talk and the wonderful teaching that she has done this evening. And thank you everyone for joining us. So don't forget to join us again in a month on the 10th of March. We'll see you here at the same time. And until then, hope you all will stay safe and take care. So thanks again, Jen, and thanks again to everybody. I'll end the meeting here.
Thank you, Sabrina.
Thank you. Bye, everyone.